So hi, in this video we are going to discuss about electric flux and Gauss law. Electric flux and Gauss law. So in order to understand Gauss law, it is required to understand electric flux. So electric flux is basically rate of flow of electric field lines. Rate of flow electric field lines through a surface, and this surface can be like open and closed. So let's understand it in the better version. So suppose these are the electric field lines. This is electric field lines, and a surface is placed inside it. Like this is the surface. This is the surface which is placed inside it. It's having like area A, the whole area A, and I talk about area element. Another color, area element. It is dA, and the area vector is perpendicular to this surface. So this is area vector dA, and these are the electric field lines. E vector is in x-axis. So electric field is like this, and the area vector is this. So flux is defined as electric flux is defined as number of field lines passing through this small area element dA. This one is given by E and dA cos of theta. This is dot product of this E dot dA. In another words, we can write it E dA cos of theta, and this is E dA. If I want to want the whole flux passing through this whole area, small dA, small dA, small dA everywhere, I have to integrate it E dA and cos of theta. So flux can be written in this manner. So electric field is constant. This will come outside the integration, and it can be written as E dA cos of theta. So this is phi. Okay. I will call this equation. And let's understand in better version by one or two more examples. So let's take a case one. So these are the electric field lines again, and there is some area A. Wait. This is the area A, and this is small area element dA, which is and area vector which is perpendicular to this area, and this is electric field E. So flux phi in this case can be said as E dot dA. So is E dot dA and dA vector, and this is mod of E, mod of dA, and this is cos theta. But theta in this case is 0, like electric field and area vector is in same direction. So we can write it, and E dA cos 0 is 1, and electric field will come outside because it's uniform everywhere on the surface, and dA. So it's E dA is A. So flux phi can be said for this case one is EA, and we will discuss this discuss the case again. And let's say this is case 2, and like again the electric fields are like this. And the surface which is kept inside this is like this, having a certain angle. This is dA, this is dA area vector. These is electric field lines E. Suppose it is like at 60-degree angle. So phi can be said as E dA cos 60-degree. So to find out the total flux phi, E will be outside because it's uniform. dA, the like whole area, small area, this is A, and cos theta by 2 is 0. So in this case, the flux phi will be EA by 2. And let's discuss the case 3. Case 3 in which we will put the small like, plate in this direction. This is the same. This is plate inside the electric field like this. And the area vector of this is dA vector, and electric field lines is in this direction. So phi is E dot EA. EA cos 90, right? And this is 0. So no field lines are passing through this plane when it is kept parallel to the electric field. So we discussed 3 cases like this. So now we are in the stage at which we can understand the Gauss law. So let so to understand the Gauss law, we will start from like a very basic an example. So in this example, we take this is the plus positive charge, and this is kept inside the sphere. This is in 2D, but consider it in 3D. Okay, and this is like positive charge plus is inside the sphere. So as we have seen, like flux phi can be written as E d phi, E d A cos of theta. But like electric field lines from this charge is like in this direction for every point. It is like this. So an area vector is perpendicular to the surface, and this is like this. Means electric field and dA are in same direction. So the angle between them is 0. So theta is 0. So the flux d phi can be written as E dA cos 0 degree. So electric field is continuous here, like the continuous, and these are equally spaced. Means this charge and this surface is equal, and as I talk about this is also equal. So this is equal means it's not changing upon like this for the distance. So is this I will this will come outside the integration, and this is in cos 0. So it is EA, and electric field can be written like for the charge particle is Q, and electric field can be written as E is 1 upon 4 pi epsilon naught Q over R square R cap. R square is distance from the charge where we want to measure the electric field. Like for this charge, this is R, and R cap is in direction of this measurement. Like this is in R cap direction, and this is charge Q. and epsilon naught is permittivity of free space. And so let's write E is 1 upon 4 pi epsilon naught q over r square. If I want to measure the flux passing through this sphere, and this sphere is of radius capital R, so I will write this is on capital R square, and area of this sphere can be written as area of sphere 4 pi capital R square. So multiply it 4 pi capital R square. So 4 pi get cancelled out, and R square also gets cancelled out. It we find that Q over epsilon naught. So flux phi we get is Q over epsilon naught. So now question arises, why what if I put like one charge here, I put here one charge, and more charges plus plus plus. What will be the situation then? When we will call it like the Q enclosed, the sorry, flux phi is equals to Q over epsilon naught, and the Q is will be summed over, means like add every charge which is present at the center or inside the sphere anywhere. We just need to sum it, and then we will get our desired result. So okay, and here like epsilon naught is a permittivity of the free space, and if what if I get like after the calculation sometime flux zero flux meaning zero flux means there is zero flux means there is no charge inside. It's not like that. Zero flux means there can be no charges, there can be charges, but equally positive and negative are equal. Like there is two electron positive and two electron negative, so the total flux is zero. And if there is no charge, obviously there is flux phi is zero. So this is meaning of flux zero. So this is called as Gauss law. So Gauss law is basically flux phi emerging out from the closed surface is equals to total charge enclosed inside it multiply with 1 upon epsilon. This is typical Gauss form. Gauss, or this can be said as derivation of Gauss law as well. But Gauss law is not valid or can't be used for each and every case. We can use Gauss law for certain cases only. Uses of Gauss law. So we can use Gauss law in three cases, in three particular symmetry. One is spherical, which we have seen earlier, spherical symmetry. Second is cylindrical symmetry, and third is planar symmetry. So first is spherical symmetry. In order to understand spherical symmetry, let's discuss a same case again. So assume that this is the sphere, okay, and this has some charge density positive on it. And like there are three cases. This is the center of sphere, and what if I want to find the electric field inside this sphere? So this is, let's say this is R1, and I want to find electric field outside this sphere. Oh, this will be fine. Okay, and this is of radius R. So the situation is clear. There is sphere of radius R. This is sphere of radius R having charge Q on it, and this is small R1 radius sphere inside it and capital R2 radius outside it. So like we know that phi is equals to integration E dot dA is equals to Q over epsilon. This is form of Gauss law, and this here the this integration is over close this path. So for it we divide into two cases. The case first is for radius R1. R1 flux phi we want to say E dot dA. So E electric field and E dot dA. And for this, I we want like what is the charge inside this sphere? So there is no charge inside this sphere. So this is 0 upon epsilon naught. So there is no flux passing, no flux, no phi flux passing through sphere of radius r1. And similarly, we should talk about like case 2, and case 2 is of radius. What about radius r2 sphere? So flux is E dot dA summation q over epsilon naught charge inside this sphere r2 sphere. So if this is charge q is uniformly distributed over radius r, so we should call it q, and this is epsilon naught. We should mention here also that this charge is capital Q distributed on the surface of sphere radius r. So for this E is uniform because it's like centric and every distance here is equal, and this is E dot dA, and electric field dA is upon 4 pi over r2 square. This is Q over epsilon naught. So electric field can be given as Q over 4 pi r2 square epsilon naught into r. This is the thing which there. If you want to find out the electric field here, and this is so on. So this is form of electric field. By using Gauss law, we can find the electric field, flux, and all these things. And if I multiply this E with the sphere area 4 pi r2 square, this will give me flux. Okay, that's right. Now this case, let's discuss the cylindrical case as well. Second cylindrical case. So like for the cylindrical case, let's assume like there is a rod of charge, a charged rod. This is plus charge, and it is required to find the electric field due to this charge rod. Is okay. So according to the Gauss law is simply E closed E dot D, because like we this is surface and charge is inside it, so we are talking about closed charge. This is Q over epsilon naught. Okay. So electric field is same at every distance from this wire. So this is E outside dA, and this is charge Q, and this is like lambda charge density, lambda charge density wire. So this is lambda charge density wire. So and this length is capital L, I assume. So the net charge inside this cylinder is lambda into L. Lambda into L is net charge, and this is divided by epsilon naught. So E dA is area of this cylinder. Cylinder's area is 4 2 pi r into L, and this is lambda into L over epsilon naught. L cancel out, and E comes here from lambda over 2 pi r epsilon naught. Here r is radius of this cylinder. This is the electric field due to wire. We solved it by considering the symmetry of cylindrical case. Let's discuss the last case, which is planar symmetry. Planar symmetry. To understand this planar symmetry, assume this is the surface, and charges on the surface is plus charges distributed everywhere. And if we need to say what is the charge density on it, so charge density say is sigma. Sigma is like total charge over q by a. This is total charge. Okay. To find out the electric field, now it is required to construct a Gaussian surface. We will understand the Gaussian surface. Assume this is like in cylinder is like inside it, just inside it. This is and this is this is the cylinder, and Gauss law is phi E dot dA is q over epsilon naught, and we can say break this cylindrical area in like three area surface. Like say this one is area 1, this one is area 2, this is area 2, and this is area 3. So area 1, area 2, and area 3. So electric field, this is charge. So electric field is in this direction due to this charge. This is electric field, electric. So this is charge, and electric field is perpendicular the surface. This is perpendicular the surface, and similarly, electric field is like in this shape. So if we break it into like three regions, 1, 2, 3, for both of these, like area 1, area 2, and area 3. So electric field in this direction for area 1. So E and EA1, E and A1 has theta is equals to 0. And similarly, E and A2 has theta is equals to 0. But E and A3 has theta is equals to 90. So there is no need to calculate this third integration. This is automatically 0, q over epsilon naught. So what if I integrate over this? So E D, let's call it dA, and the same area is below this dA. So dA plus E dA is q upon epsilon naught. The electric field is this is same distance above and same distance below. So electric field is same. So this is uniform. Come outside E dA plus E dA is equals to q over epsilon naught. So this is E into area A, same direction, E this direction and dA is this direction. So and E is in the direction and dA is in the direction. If this is opposite, like dA is in the direction and electric field is in this direction, so this will be negative. And this is for better understanding. So this is EA, and similarly this is 2 times 1 and this is 2. So 2 times EA is equals to Q over epsilon naught. So this is E is equals to Q over 2A epsilon naught. And in another words, Q can be written as like where I have written Q can be written as sigma into A. Okay, the sigma into A equals to A epsilon naught. So area got cancelled. This is sigma over 2 epsilon naught. This is electric field. So electric field due to this planar sheet can be said as E is equals to sigma over 2 epsilon naught. So let's assume like there are two charge plates, same type of thing which we have mentioned above, and this is negatively charged. This is positively charged and this is negatively charged. So electric field in will be due to this wire one, sorry, in one P1 and this is P2 will be in this direction. This will be like this. And the value of this is E over 2 epsilon naught this direction. And for this negative one, because positive electric field due to positive charge is like this. And for the negative charge, it comes towards the field. Or it covers towards the negative charge. It is like this. So this is like this. So this have same charge density minus sigma and plus sigma. So the electric field is this is plus sigma over 2 epsilon naught and this is minus sigma over 2 epsilon naught. So electric field in this area is 0. And what about this area? This area is electric field is sigma upon epsilon naught. And about this area again electric field is 0. So electric field is sigma upon epsilon naught between the plates. So this is the capacitor and electric field inside it like given like this.